Okay, last one. So we've got free energy of dissolution. A little bit of review because I'm going to use these pictures that we used before. Breaking up solute is like this. Solid's going to individual particles like gases. Breaking up the solvent is like going from a liquid form to individual particles. So when we put them together, we get the solution aqueous. Now, we've looked at a little bit of this delta H before. The idea is that process 1 is going to take some energy. Process 2 is going to take some energy. Putting them together is going to release energy. If this release is less than what we put in, the change in enthalpy is going to be a positive value. Same holds true for negative. Again, the two processes take in energy, putting them together releases it. The change in solution is going to be negative. So it's going to release energy. Okay, that's the review part. Now, entropy, symbolized as S or change in entropy, delta S, what does it mean? It's the other component of if a reaction is going to occur. It's called randomness. So entropy is randomness, and it's in joules per gram. Sometimes you'll read it as places will come across and say this is disordered. That's fine. And they'll say a decrease in entropy is a more ordered situation. Instead of using different terms, I'm always going to use the term randomness. Increase in randomness, a positive delta S. A decrease in randomness, a negative delta S. Gas has more randomness than liquids and aqueous, which has more than solids. And when we keep this in mind, we're thinking about of one substance, okay? You could have something that's liquid that has less randomness than a solid, depending upon what that solid is. So we're thinking about this as one substance. So solid dissolving is always an increase in entropy, going from ordered, or I should say that, look at me go, a decreased randomness to an increase in randomness, positive delta S. So when we think of free energy of dissolution, the universe tends to release energy and more randomness. That's a general concept. Free energy is the energy relationship between enthalpy and entropy. If the overall change, according to this equation, is negative, it's spontaneous, which means it's likely to occur. Since things dissolving are always going to be increase in randomness, it'll always be positive. So S is always going to be positive for something dissolving. This aids in making delta G negative. So keep that in mind. Just think about this in concept. If something will dissolve, delta S is always positive, which puts us in a great area for delta G being negative. And remember, delta G being negative means the salt will dissolve. However, remember that delta H we talked about? Sometimes it's positive, sometimes it's negative. Depends on the temperature. It makes a big difference. We actually need to see if something does dissolve based off the actual values. Okay? When something dissolves, it can feel hot or cold. Why? Because hot and cold deals with delta H, not delta G. Delta G is like a comparison between two things, between these two. And if the overall comparison is negative, this will occur. There will be a net release of energy, and that is what we're looking for. That's what this universe is looking for, is to be a release of energy. It's already got the increased randomness by dissolving, separating out. But what we need to see is that how do these come together? And we can't really do it unless we have actual values to see if that occurs. Because again, some things dissolve. Sodium chloride has a pretty high delta G because it dissolves easily. Its delta H must be very negative, minus. Again, this will be a positive value, so it's only going to get more and more negative. Something like lead-2 iodide and the KSP values we saw that were very small, these are going to be negative, but this must be pretty positive to occur, so very little of it occurs. Coming with any kind of questions, and this will be the end of Unit 7. Take care.